Alright, video number 5 is called the Intro to the Binomial Distribution. Now, really, what we're going to do in this video is a lot of review of stuff that we've done in the past, but what we're going to do in the next couple videos is basically show you shortcuts of how to really incorporate this thing called the binomial distribution into certain problems that follow a binomial distribution. Just like really we can only use normal CDF and z-scores with normal distributions, you can only do binomial distribution stuff with cases that follow the binomial distribution. Now, situations that have only two outcomes. This is what we're going to be following with a binomial type of distribution. So flipping a coin, there's only two outcomes, heads or tails. Having a child, boy or girl. Reading digits from a random number table, even odd. I mean, we could even talk about countless other situations where there's only two outcomes. Okay, and not only are we going to talk about binomial distributions, but later on in this section we will also discuss things called geometric distributions, which are very, very similar to binomial distributions with one slight difference. Okay. Now, in the binomial distribution, bi means two, nomial means numbers or numerical outcomes, and distribution means we're going to list the outcomes and their probabilities. Just like when we did a probability distribution, when we would make our table, and we would have all of our x outcomes, and then all of the probabilities tied into them. Okay, so we're still going to do the same type of thing, but with a binomial distribution instead, more specifically. And there are four conditions for calling a situation binomial, okay? And you're going to have to memorize these four conditions. First condition, that there's only two outcomes. Something that you're going to call a success and something else that you will call a failure. Number two, there is a fixed number of trials or observations. For example, flipping a coin. You would say that I'm only going to flip a coin 10 times, and that's it. That's a fixed number. Okay, or if you say, I'm only going to have 4 children, you are fixing the number of children that you plan to have. Number 3, the observations are independent. So, for example, each flip of the coin is independent of each other. Each child that you will have is independent of the previous children that you have had. And number 4, the probability of success is the same for each trial or each observation. So with the coin flipping, the probability of, if we call heads a success, the probability of a head stays 50% regardless of what happened the time before. Boy or girl, 50-50 chance. Even and odd is a 50-50 chance. Not all binomial situations, though, involve a 50% success and a 50% failure. And we will look at an example in the notes here. So again, these four conditions you absolutely must have memorized. Okay? And if any one of these conditions are not met, then it is not a binomial distribution type problem. Okay, so if the four conditions are satisfied, then x is the number of successes. So you could say, if we were going to flip a coin 10 times, I want to know what's the probability that I will flip exactly 6 heads out of 10 coin flips. So that is something we will examine more in depth specifically. So x, our number of successes, is called a binomial random variable. Not just a random variable anymore, but specifically a binomial random variable. And the probability distribution of x, our table, is going to be referred to as a binomial distribution. The binomial distribution is the count of successes. That's what we're going to be kind of focusing on. The parameters or variables involved here will be n and p. And n is going to represent the number of trials. How many times are you going to do something? And p will represent the probability of success. Okay, and the three examples we talked about on the previous page, the probability of success was always 50%. But again, I said it's not always going to be 50%. Now, a shortcut way of writing a binomial distribution, just like we said we could write the normal distribution like this, where the capital N stood for normal, with a mean of whatever, mean mu, and standard deviation sigma. The shortcut way of writing the binomial distribution is a capital B, and then in parentheses, N, the number of trials, and P, what's the probability of success. Okay, so oftentimes you might see this notation used to describe a binomial distribution. When counting x number of successes, the possible values of x are 0. You could have a chance where you don't have any successes. 1, 2, 3, all the way up to n, your number of trials. If you're going to flip a coin 10 times, there is a chance that in 10, you could have 10 heads out of 10 flips. Okay, so it's 0 all the way up to however many times you're doing whatever. Okay, so a couple wanting to have 3 children, all girls, has a binomial setting. The number of trials, the number of children, would be 3, and the probability of success for each girl, in this case, for each child, is 50%, or 0.5. Flipping a coin 10 times and counting the number of heads. Well, the number of trials we just mentioned here is 10 times, and the probability of success that we're considering heads is 50%, or 0.5. Okay, so an example might say a distribution follows this setting, and then they might ask you a question related to it. So you need to understand really what this is saying statistically, mathematically. All right, so an example. The Farrells have 3 children, Jennifer, Jessica, and Jacqueline. If we assume that a couple is equally likely to have a boy or a girl, then how unusual is it for a family like the Farrells to have 3 children who are all girls? Okay, so first, is this a binomial type problem? Are there 2 categories? Yes. Maybe, yeah. Success, we're going to consider a girl. A failure, we have a boy. Or do we have a fixed number of trials? Yes, we have 3 children. So n equals 3. Are the n observations independent? Children are independent from each other. Just because you have 2 girls doesn't mean you're due for a boy. So yes, all our children are independent of each other. And is the probability of success the same for each trial or each child? Yes, the probability of having a girl is 50%, because we said up here, if we assume that a couple is equally likely to have a boy or girl, so that maintains our 50% probability of success. So do we have a probability or a binomial distribution here, or do we not? We do, where n is 3 and p is 0.5, or 50%. So now, to jump off this, when a couple plans to have a child, how many outcomes are there for the sex of our 3 children? So the first child, we have 2 choices. We're either going to have a boy or a girl. Second kid, third kid. So altogether, we have 2 options, 2 options, and 2 options. We said we may multiply those together. And we really have 8 outcomes here to have 3 children. Okay, some of them could be boys, some of them could be girls. They could be all one sex, so we're going to make a tree diagram for all of our possibilities. So our first kid, boy or girl. From there, we're going to start branching. So the second child, boy or girl, boy or girl. Third kid, branch off again. And now we're going to look at each branch of our tree diagram. So in the very top one, it's saying we have a boy, and a boy, and a boy, which means altogether, we just had 3 boys. And if I keep continuing down the line here, there are all 8 of my outcomes. Now, typically I would say, you cannot just say that each one of these has a 1 in 8 probability. But in this case, we can. Because the probability of having a boy, we said, was 0.5, and a girl was 0.5. So every one of these boys and girls are exactly the same probability. So the probability of having a boy, and a boy, well, the probability is 0.5 times 0.5 times 0.5, which is really just 0.5 to the third power. Having a boy, and a girl, well, is 0.5 times 0.5 times 0.5. It's the same thing. So really, all 8 of these outcomes, put my third power inside the parentheses, meant to technically put it outside the parentheses. All of these really have the same probability of occurring. Now, if we jump down here to our binomial distribution, we said where x is going to be the number of girls, or our successes, we can have 0 girls, 1, 2, or 3 girls. Now, having no girls, well, that happened one time, right here. Okay, and 0.5 to the third power is 1 and 8. If you took 0.5 times 0.5 times 0.5, you will get 12.5%, 0.125, which is that 1/8. Now, having one girl, well, how many different ways out of our 8 were there of having one girl? Well, here's 1, here's 2, and here's 3. It's whether the girl is the youngest, the middle, or the oldest child. Okay? And each one of these have a probability of 0.125, our 1 and 8. So the probability of having one girl is really a culmination of all 3 of these possibilities here. Now, all of these possibilities are disjoint events, so you may add them together. So 0.125 times 3, essentially, gives us a 3 in 8 chance, which is 0.375. Okay, having 2 girls. Well, it can be this, this, or this. So we're going to end up with the same exact probability as we did for one girl, 3 out of 8. And having all 3 girls only happened one time, 1 out of 8. So again, if you took 0.5 to the third power, it is 1/8, which again, let me put all the individual probabilities here. These are all the decimal equivalents of the fractions. And if you were to add together all 3 or all 4 of these probabilities, you would end up with your 100%. So we know it's a valid probability distribution. Okay, now here's an example of where the probability of success and failure is not going to be 50-50. Okay. So in this example, we're going to take a 6-sided die, regular 6-sided die, and we're going to roll it 3 times. And we want to find the probability of rolling exactly 1, 4. So to solve this problem, we're going to draw a tree diagram. And what we're going to consider a success is a 4, and not a success, a failure, is going to be rolling not a 4. Okay? Now, we can't say a 1, 2, 3, 5, or 6 because those are 5 things. And for a binomial distribution, we can only have 2 outcomes. So we're going to make our success rolling a 4. So here's where I'm going to say that, and then I'm going to put an N for not a 4. Okay? So for my second roll, I'm either going to roll a 4 or not a 4. And again, for my third roll, I'm going to roll a 4 or I'm not going to roll a 4. So here are all my outcomes. Again, I'm going to follow all the branches of my tree diagram. So here's rolling a 4 and rolling a 4 and rolling a 4. So I've rolled all 3 4s in a row. Here's rolling a 4, and then not a 4, and that's where I get that from. Here's rolling not a 4, a 4, and a 4, and that's how I'm getting that outcome there, and all the rest in between. Now, you might say, oh, go back here, there are 8 total outcomes here. So the probabilities are going to be the same as they were for the 3 kids, but they're not. Because the probabilities for rolling a 4 and not rolling a 4 are not 50-50. So let's backtrack a little here. There we go. So the probability of rolling a 4 on a 6-sided die, you've got a 1 in 6 chance, which means you have a 5 in 6 chance of not rolling a 4. And so rolling this 4, 1 in 6, not rolling a 4, 5 in 6, 1 in 6, 5 in 6. And I don't really have enough space to really write the 1 out of 6, and 5 out of 6 there. But you get the idea. So rolling 3 4s in a row would be 1/6 times 1/6 times 1/6, which ends up being 1 in 216. And if you wanted to write that as a decimal, you certainly could. I'm just going to leave these as fractions. And then rolling a 4, and not a 4. Well, that's going to be a 6th times a 6th times 5/6 for that not a 4, which is going to be 5 in 216. And if I keep going down the line here, we find the most common occurrence is not rolling any 4s. Rolling 3 non-4s. We have a 125 in 216 chance, which is greater than 50%. Alright, so now we're going to come down here and fill out our table. So what's the probability that we get 0 4s? Because that's what we're considering a success. Our random variable x is getting a 4. So getting 0 4s, well, there was only one way that happened. And we said that's the probability, 125 out of 216, which is 57.9%. Getting 1 4, well, it either happened here, or it could happen here, or it could happen here. Either the 4 was the first, the second, or the third roll. Now, each of those 3 outcomes have a 25 in 216 chance. And all 3 of those outcomes are disjoint events, so we may add together all of those individual probabilities, which will give us a 75 in 216 chance, which is a 34.7% chance for 2 4s out of 3. There's 2 4s, there's 2 4s, and there's 2 4s, which all relate to a 5 in 216 chance. And again, since all of those are disjoint events, either this will happen or this will happen, I can add my 5, 5, and 5 to get a 15 out of 216 chance, which now we're talking about approximately a 6.9% probability. And last but not least, getting 3 4s out of 3 rolls, well, that only happened one time, and there's our probability, 1 out of 216. Okay? So, to answer the question that's up here, what is the probability of rolling exactly 1 4? That would be this, which is this. This would be our answer right here. We have a 75 in 216 chance of rolling exactly 1 4. Okay? And there were 3 ways we could roll that 1 4, which was this, this, and this. And that's why we had to add together those probabilities, because I didn't specify where that 1 4 had to end up at. Now, if I said, what's the probability that I roll exactly 1 4, and it's on the first roll, well, then that would be this answer, 25 out of 216. But if I don't specify where I want to see the success, then you have to consider every possibility that would be considered a success. All right, so now I converted all those into decimals, those probabilities. So what's the probability of rolling exactly 1 4? We said that was our 34.72% here. What's the probability of rolling more than 1 4? Now, more than one 4 is going to specify 2 or 3. Now, either I will roll two 4s or 3 4s. Those are disjoint events, so I may add together their probabilities, and if I do so, I get approximately 7.4%. For number 5, what is the probability of not rolling a 4? Well, that's this value right here, 57.87%. Use the information in the probability distribution table up here to create a probability distribution histogram. So, if we talk about probability being our y-axis, as it always is, notice I went by 15% here, just because I knew my maximum was this, and my minimum was, well, it's almost 0. So my maximum is what kind of decided my spacing here. And then down here we have our x random variable of having 0, 1, 2, or 3 4s in 3 rolls. And if I now take my 4 probabilities here and fill them in, I have a very strongly skewed right distribution. Does that mean that all binomial probability distribution histograms will be strongly skewed right? No. It just happens to be that this one happens to be strongly skewed right. If you did a probability distribution histogram for the 3 children scenario, you would find that it is symmetric or approximately normal. Okay, so every problem will be different in terms of its histogram. And that is the end of video number 5. We will see you for video number 6.